Hi, dear audiences, welcome to our show. This channel provides knowledge of power systems for insiders, and our team is committed to offer professional explanations and answers. Today we will explain some knowledge about soft leads. In last program, I briefly introduced you hard leads. Today, let's know about soft leads, which connect generators or transformers to various electrical appliances. Compared with hard leads, soft leads are cheaper and easier to be installed. What are the requirements when choosing qualified soft leads? Firstly, the lead's cross-section and structure are determined by its application environment, such as ambient temperature, sunshine, wind speed, pollution, altitude, and loop load current, corona, radio interference, and so on. Please note, anti-corrosive aluminum or copper-stranded lead should be chosen if it is used in coastal areas with high salt content in the air, or other places where the surrounding gases are apparently corrosive to aluminum. Secondly, the load current going through the lead matters. When the load current is large, choose a lead with larger cross-section. When the voltage is high, in order to maintain the electric field intensity of the lead surface, pay attention to the minimum cross-section of the lead to meet the requirements of the corona. Therefore, increase the outer diameter of the lead or the lead number of each phase according to the specific needs. When leads are used on a 330 kV distribution device, corona and radio interference are the main control conditions for choosing the lead cross-section and structure type. Therefore, the hollow expanding lead is chosen. This kind of lead has the advantages of light unit weight, uniform current distribution, no need for spacer on the structure installation, convenient connection of fittings, and no additional tension caused by the short circuit of the split lead. When used on a distribution device of 500 kV and above, split lead should be used, since a single hollow expanding lead can no longer meet the requirements on corona and other conditions. When mentioning the split lead, you may think of its defects, such as large tension, complicate fitting structure, and complex installation, but at the same time its advantages of improving the lead's natural power and reducing electric field intensity on the lead surface make the split lead composed of hollow expanding leads or extra light leads the best choice for 500 kV distribution device. In particular, either dual split hollow expanding lead or 4 split extra light lead or 4 split hollow expanding lead can be used on a 750 kV distribution device. For a 1000 kV distribution device, only 4 split hollow expanding lead can be used. What are the specific characteristics of split lead? It is known that if a single soft lead or expanding lead can't meet the requirements of large load current, corona, and radio interference, split leads with lower cost and stronger shock resistance than the busbar is suitable to ultra-high voltage distribution devices. According to load current and voltage, forms of split leads can be divided to horizontal dual split, horizontal tri-split, equilateral triangle split, 4 split, and so on. The carrying current of horizontal tri-split lead is about 6.5% lower than that of the equilateral triangle split, and the maximum electric field intensity on its surface is about 4.5% higher, but its fitting connection is easy. Therefore, the horizontal tri-split in the inlet and outlet circuit with relatively small load capacity and more T-connection leads are used on some 500 kV distribution devices, while equilateral triangle tri-split are used for the main bus with large load capacity. At present, 750 kV distribution devices commonly use dual split leads, and 1000 kV distribution devices commonly use 4 split leads. Due to the adjacent thermal effect of split leads with different arrangements, we should consider the carrying current of split lead affected by the lead arrangement, lead number, and lead spacing in the actual carrying current of the split leads should be calculated according to the carrying current of n single leads multiplied by the corresponding adjacent effect coefficient B, namely, in this formula, N represents the number of split strands of each phase lead. I_SHU represents the long-term permissible working current of a single lead. B is the proximity effect coefficient. The splitting spacing of the split lead is mainly determined by corona check results. For example, the spacing between dual split leads of 220 kV and below can be 100 to 200 mm. The spacing between double split leads of 330 to 750 kV can be 200 to 400 mm, and the spacing between 4 split leads of 1000 kV can be 600 mm. Among them, if dual split leads or tri-split leads arranged in equilateral triangles are used on 500 kV distribution devices, the split spacing D equals 400 mm. If horizontal tri-split leads are used, the spacing D equals 200 mm. The minimum diameter of the subsidiary lead is determined by corona and radio interference. According to the calculation, on the condition that tri-split equilateral triangle arrangement and the dual split horizontal arrangement are adopted and the split spacing is 400 mm, the minimum diameter of the subsidiary lead for the 500 kV distribution device is 2.95 cm and 4.4 cm respectively. However, under the requirements of wire production specifications and certain safety margin in our country, the minimum diameter of tri-split and dual-split subsidiary lead should be 3.02 cm and 5.1 cm respectively in production. In addition, it is also necessary to determine the length of the subsidiary spacing. The length of secondary spacing refers to the installation spacing of spacer. When determining the spacing of split-lead spacers, we need to consider the impact of the magnitude and time of short-circuit dynamic tension on the frame and electrical terminals to avoid the critical point of maximum dynamic tension. For overhead leads, the spacing of spacers can be larger value, and the spacing of connecting leads between equipment can be smaller value. Specifically, the length of the subsidiary spacing is mainly related to the following four factors. Factor 1. Short-circuit tension. The stress of a dual-split lead in short circuit is different from that of a single lead. A single lead has only interphase repulsion, but a split lead not only has interphase repulsion but also the electromagnetic attraction between the subsidiary leads in the same phase, which will cause the secondary wires to be stretched, resulting in elastic tension. This force is the first maximum tension of the split lead. At the moment short circuit occurs in the split lead, there will be a first maximum tension which greatly affects the strength of lead, insulator and frame. The first maximum tension of the split lead within a subsidiary distance is mainly related to the length of the subsidiary lead, the magnitude of the short circuit current, the split spacing and the split lead's initial tension before the short circuit. The repulsive force between phases is called the split lead's second maximum tension. Since the maximum values of these two forces occur at different times, the strength bore by busbar system and frame shouldn't be superimposed. In engineering design, the first maximum tension should be used as the basis to estimate the lead's short circuit tension. Factor 2. The magnitude of short circuit current. Since the dynamic tension caused by the lead in short circuit is proportional to the square of the short circuit current, the development of the power system should be considered when determining the length of the subsidiary spacing and verifying the dynamic tension, and the length of the secondary gap should be determined according to the value of the most likely short circuit current. The length of the subsidiary spacing is determined according to the most likely short circuit current value. Factor 3. The permissible contact state of the subsidiary lead during short circuit. Generally, in power generation and transformation projects, short-circuit collision is not allowed for split leads composed of expanding leads, but it is theoretically allowed for split leads composed of other leads to reduce the number of spacers. It is worthy note that a spacer should also be placed at the connecting metal fitting of the busbar down lead to prevent the damage of the metal fittings to adjacent leads. For connecting leads of electrical equipment or short, the equipment connecting leads are densely covered with spacers to ensure that subsidiary leads are in the non-contact area during short circuit to limit the first maximum tension within the allowable tension range of the post-insulator or electrical equipment terminals. Factor 4. Limited force on frame. In a certain splitting distance, there are two ways to reduce the maximum tension. The first is to shorten the length of the subsidiary spacing making leads in the non-contact area. The second is to increase the length of the subsidiary distance making leads in the contact area. In engineering design, it is necessary to check the curve of the maximum tension in the length of the subsidiary distance according to the selected lead type, span and short circuit current to reasonably limit the frame strength and decide the length of the subsidiary distance. The above points are what we need to pay attention to when knowing about soft leads. Hope our explanation can offer you some help. This channel will update more videos of power system in future. If you are interested in our videos, please follow our account to avoid missing more contents. If you don't like our videos or have any advice, please let us know. Thank you for your watching and see you next time.